Consider this before viewing space, distance, and time. Our solar system stretches for billions of miles, but it is minuscule in the context of the Milky Way galaxy. What do you know about the extreme distances of planets and stars in the universe? As you watch the program, note the many scales of measurement used to calculate the distances between planets, stars, and galaxies. Assignment Discovery now presents Space, Distance, and Time.
Since the time of the ancient Egyptians, the skies have changed, but the questions they inspire are the same. How vast are the heavens? How old is the universe? Questions that take us to the outer reaches of space. In the quest to put a yardstick across the universe, the moon is our first measure. It is our only natural satellite, just 238,000 miles away, a trivial distance on this scale. In fact, to measure the heavens, astronomers had to invent an entirely new unit of measurement. It's called a light year, the distance light travels in 1 year. Light travels at 186,282 miles per second. So 1 light year is equal to 5.88 trillion miles. Our moon is barely more than a light second away. Our sun is a bit farther. The sun is, on average, 93 million miles away from Earth. Its life-sustaining light takes just over 8 minutes to reach us. To the planets at the outer reaches of our solar system, the sun is just a brilliant star. Neptune is about 3 billion miles from its warmth. Sunlight takes 4.5 hours to arrive here. Outside our solar system are the stars, whose patterns in the sky appear to be two-dimensional to the naked eye. But now, thanks to quantum leaps in astronomy, many stars are within our grasp. We can determine their age, their composition, and their distance. If you don't count the Sun, our nearest star is Alpha Centauri. It's the big one to the left. But your eyes are playing tricks on you. Alpha Centauri is more than just a star. It's even more than two. It's a triplet. This stellar trio is 25 trillion miles from Earth, or, as astronomers would put it, 4.3 light years. Out here, our sun is nothing but a dot, a modest star visible to the naked eye. Onward and outward, and some 200 light years from home, is W Ursa Majoris. It's a cosmic Siamese twin, two stars that are near enough to exchange materials. Go farther, and you reach the stars of the Orion constellation, which from Earth appear to be a flat pattern. Out here, we realize that the stars of the Hunter's Belt lie at vastly different distances. To reach the heart of Orion takes 1,500 light years from Earth. Come that far, and you reach the Orion Nebula. This great cloud of dust and hydrogen is what's called a stellar nursery, a cocoon of gestation, a place where stars are born. Keep traveling at the speed of light, and you'll eventually reach the center of our own galaxy, about 30,000 light years away. If we go beyond it and look back, you can observe a spiral, thought to contain at least 100 billion stars, the Milky Way. But as vast as the Milky Way seems to us, it is just one in a local group of galaxies. That group, in turn, is part of a bigger group, a supercluster. Superclusters form webs, networks that cross the universe. But there is more to the cosmos than meets the eye. Over 90% of its mass is invisible. It's called dark matter. It may fill the space between galaxies in the universe, and it's unlike anything else we've encountered before. It doesn't give off, reflect, or absorb light. In fact, some astronomers aren't even sure it's really there. But for now, let's return to our own galaxy. A beam of light takes 100,000 years to cross the Milky Way. Gaze up at the faintest stars you can see. Their light has taken centuries to reach you. What you're actually looking at is a picture of those stars as they appeared thousands of years ago. Relative to the universe, our solar system doesn't seem so big. You can go from the Sun to Pluto in a matter of hours, traveling at the speed of light, of course. How do astronomers know all this? How on earth did they learn to measure the universe? The story begins in Egypt more than 2,000 years ago. It involves basic geometry, calculations familiar to ancient temple builders. The Egyptians gave the world the first unit of astronomical measurement, the circumference of the Earth. They observed that at noon, the sun shone directly down a well in Aswan, while 500 miles to the north in Alexandria, a column cast a shadow. Why the difference? According to legend, a librarian called Eratosthenes realized it was due to the curvature of the Earth. When the sun was directly overhead in Aswan, it was at an angle in Alexandria. That caused the shadow. The difference in angle was 1/50th of a circle. So, the distance between Aswan and Alexandria must also be 1/50th of something. Eratosthenes guessed that it must be 1/50th of the circumference of the Earth. And he was right. The Earth's circumference is about 25,000 miles. 200 BC, and it was known that the Earth was an orb in space. Where it lay in space was tougher to figure out. Ancient humans believed the Earth was at the center of things. Around it, set in a series of crystal spheres, orbited the Moon, the Sun, the planets, and the stars. But the planets were a puzzle. They were called wandering stars. Their progress through the heavens could be erratic. Some would stop, reverse, and proceed again in a pattern now known as retrograde motion. Around 100 AD, the Greek astronomer Ptolemy had an answer. He accounted for their wanderings with epicycles, little orbits made by the planets around their main orbital paths. It's a clumsy idea, but it seemed to fit the observations. Ptolemy's theory appears to work for planets like Venus and Mercury, which speed across the sky at twilight. But it fails with others like Mars. For 1,400 years, there was no progress. Then a Danish astronomer named Tycho Brahe came up with half a good idea. He still had the sun going around the Earth, but he had the planets going around the sun. The passage of a comet sparked his theory. Observing the Great Comet of 1577, Brahe calculated that in one night its movement against the background stars was much less than the Moon's movement. This put the comet far out among the planets, smashing the notion of crystal spheres. But Brahe was still convinced that the Earth was the center of the universe. In 1543, the Polish astronomer and cleric Nicholas Copernicus put Earth in its place. He proposed that the Sun was the center of our solar system, but he assumed that the orbits of the planets were circles, and he couldn't explain the eccentric loops of Mars. It wasn't until Galileo refined the telescope in 1610 that new details of the night sky came into view. He discovered craters on the surface of the Moon, blemishes on the Sun, and several moons revolving around Jupiter. German mathematician Johannes Kepler completed the puzzle in the early 1600s. He figured out that the orbits of the planets are not circles, but ellipses, and that the speed of the planets depends on their distance from the Sun. The first accurate picture of our solar system was finally in place. Enter the English scientist Isaac Newton in the late 1600s. Newton explained more about the planets' orbits with his famous theory of gravity. He imagined a cannonball fired from a mountaintop. Fire it faster, and it goes farther. Fire it fast enough, and it goes into orbit. It becomes a satellite, like the Moon around the Earth. Newton's genius was to recognize that the force that makes a cannonball fall to Earth is the same force that governs the motions of moons and planets. It's the force that dictates the speed of orbits. In the solar system, the closer a planet is to the Sun, the faster it must move to resist the Sun's gravitational pull and stay in orbit. And it's the same force that boosts spacecraft as they explore the planets. By the end of the 1600s, astronomers had a map of the solar system, but it was a map without a scale. That began to change with the study of Venus. The dot is Venus in transit, crossing the face of the Sun from our perspective. Seen from two different places on Earth, Venus makes two different tracks across the Sun. Using trigonometry, astronomers could judge Venus's distance from us. Similar calculations using the other planets helped provide a scale for our solar system. Measuring the distances of stars would be trickier, though. As our planet circles the Sun, we would expect the nearer stars to move from side to side as our perspective of the cosmos changes, just as nearby objects appear to move when viewed first with one eye and then with the other eye. In 1676, a Dane named Olaus Romer was observing the eclipses of Jupiter's moons. They came sooner than expected, he discovered, when the Earth and Jupiter were on the same side of the Sun in their orbital paths. The eclipses came late when Earth and Jupiter were on opposite sides and farthest apart. The reason was the time taken by light to travel from Jupiter to Earth. Thus, Romer showed that the speed of light was measurable, not infinite. Astronomers were well on their way to coming up with the units called light years that would allow us to measure unimaginable distances. As telescopes became larger, more and more stars sprang into view. Then, in the late 1700s, English astronomer William Herschel built a huge telescope and mapped even more of the heavens. Incredibly, he counted the stars one by one. There were thousands. He produced a chart of how he thought they were arranged and put the Sun near the center. Herschel thought this was all there was of the universe. Evidence that there was more came from Birr Castle in Ireland, where the 3rd Earl of Rosse built an even bigger telescope. It was the mid-1800s, and Rosse had discerned faint, wispy clouds. He drew them. Within some clouds were strange swirls. Rosse had glimpsed what lay beyond the Milky Way. Astronomers were finally coming to grips with just how far away stars were. New, precise observations revealed that stars do shift position as the Earth orbits the Sun. It's hard to see because they're so far away. The effect is called parallax. It's measured by observing a star from one side of our solar orbit, then 6 months later from the other. How far the star appears to shift depends on its distance. The closer the star, the more it seems to shift. But scientists really got to know stars better by passing starlight through prisms. By splitting light, they could read the character of a star in the rainbow of its spectrum. The technique is still used today. Like a fingerprint, every star has a unique spectrum. Analyzed with a spectrometer, it reveals, among other things, the composition, temperature, and size of a star. Spectra fall into groupings, categories that tabulate a star's temperature and its real brightness, luminosity, as astronomers call it. A yellow star like our Sun has a luminosity rating of 1. More luminous stars shine blue, rating 10, or 100, even 1,000. And if the temperature and luminosity are known, then it's also possible to calculate the distance of a star. For instance, if we know from its spectrum that the big star on the left is 100 times more luminous than the star on the right, then why do they shine with equal brilliance? The answer is that light diminishes by the square of the distance it travels. So in reality, the big star is 10 times farther away than the little star. From the depth of the cosmos are stars that beat like a heart. They are called Cepheids. Astronomers can tell their distance from the rate of their pulse, because a Cepheid's luminosity is related to how quickly it blinks. Cepheids are celestial beacons that help measure some of the most distant objects in the sky. Cepheids beat in globular clusters, collections of stars that hover outside the main part of our galaxy. Globular clusters are too remote to measure by the parallax method, but by measuring the pulse of a Cepheid within it, a cluster's distance can be worked out. The observation of Cepheids has helped map the structure of the galaxy. The Sun isn't at the center, but 2/3 of the way to the edge. At last, the Sun was dethroned from its place at the hub of the universe. But there was another surprise. Observers have seen it since ancient times. It's a fuzzy patch in the constellation of Andromeda. Near or far, no one could tell. Then in 1923, the American astronomer Edwin Hubble realized he was looking at Cepheids in Andromeda's outer reaches. So faint, they were far beyond the stars of our own galaxy. Hubble was looking at another galaxy, more than 2 million light-years away. As Hubble peered deeper into space, he found more and more galaxies of every shape and size. Hubble unveiled an expanding universe. Galaxies traveled outward in all directions. The farther away they were, the faster they appeared to recede. The evidence was in their light. It shifted toward the red end of the spectrum, a sign of lengthening wavelengths. The wavelengths were stretching because the space between the galaxies was stretching. The galaxies were relentlessly moving apart. Edwin Hubble had stumbled upon the origins of the universe. His brilliant observations revealed an ever-expanding universe, a universe that may have had a single moment when time and space began, the Big Bang. Today, the quest to measure the universe goes on, but our instruments are crude. Observations by the world's most powerful optical telescopes have a 30% margin of error. We need finer devices. Like the satellite Hipparchus, which launched in 1997, clear of atmospheric distortion, it surveyed the nearest stars and measured distance as never before. And then there are radio telescopes, which gather radiation invisible to our eyes. The king of all telescopes is the Hubble Space Telescope, continuing the work of Edwin Hubble himself. The Hubble has studied Cepheids in a galaxy too distant for telescopes on Earth. The Hubble has returned some shocking findings. Its measurements of the most distant galaxies have told astronomers that the universe may be around 12 to 14 billion years old, almost 3 times as old as originally thought. Could the winking Cepheids be sending false signals? These Cepheid readings are probably right. It might take years to see them in context. Our picture of the Big Bang could well be way off. Indeed, when did the Big Bang really occur? And why does the universe expand? In years to come, our current ideas of the cosmos may be as quaint as those of ancient observers.
Keep watching. Discussion topics and activity and resources for space, distance, and time are up next on Assignment Discovery. Now that you've seen space, distance, and time, talk about this. Explain how 2 stars with unequal luminosity may appear to have the same brightness to an observer. Describe some factors that limit the apparent brightness of a star as seen from Earth's surface. Now try this. Locate the 5 brightest stars in your sky. Record each star's color or brightness and estimate its distance from Earth. Use a star catalog to determine how far away each star really is. Log on to discoveryschool.com for curriculum materials and resources to support space, distance, and time. To learn more, Assignment Discovery suggests The Astronomy Cafe by Sten F. Odenwald.